So today we'll be talking about the VSEPR theory. The VSEPR theory states that atoms in a molecule arrange themselves in a way that causes the least stress on the molecule itself. Therefore, you can see that atoms with 2 domains and 3 domains, respectively, arrange themselves in either a linear or a trigonal planar structure in order to minimize the repulsive forces between the ligand atoms of the molecule. So, if you have a molecule with 2 domains, they arrange themselves in a linear fashion as shown here. Now, if you have 3 domains, they will arrange themselves in a trigonal planar fashion. And you can see where the name comes from, as this is a triangle on one plane. It's also a line on the same plane. Therefore, by creating these shapes, the molecules can create the least amount of repulsive forces between the ligand atoms. The same thing applies for molecules in 3D domains. They do arrange themselves in the same fashions as shown in the previous slide, but in a 3D way. So each of these is arranged in a pyramidal fashion. If you have 4 domains, it's tetrahedral. If you have 5 domains, it's trigonal bipyramidal, which is basically 2 triangular pyramids on opposite sides. If you have 6 domains, it's octahedral. Therefore, it's 2 square pyramids. Now, the ligands arranged in a pyramidal fashion is for the same reason, to minimize the repulsive forces between them. Now, if you have something with 4 domains, you can see how arranging them in a trigonal or tetrahedral fashion will allow them to minimize the forces between each and every molecule. The same thing goes for a trigonal bipyramidal fashion and an octahedral. So not all domains are always ligand atoms. There are sometimes lone pair electrons, as you can see here. The difference is that lone pair electrons create much higher repulsive forces than ligand atoms. Because as you can see here, a bounded electron has a restricted electron or magnetic spectrum. How over here you have a lone pair, which emits a lot more repulsive forces because there's no really another area to bound it by. And therefore, they generate more repulsive force. And as a result, there are different types of names for molecular structures that involve lone pair electrons. So as you can see here, these are the different names of lone pair electron structures. Now up here, you have what we saw before, the linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral structures. These are called molecular geometries. Molecular geometries disregard lone pair electrons. So each of these individual structures, which I'll talk about later, are with regards to lone pair electrons, therefore showing the little bumps in them. However, molecular geometries for each of these are the same, because molecular geometries do not take into account lone pair electrons. Now, for a linear, if you have 2 domains, you can only have a linear structure. Therefore, there is no need to consider lone pair electrons. However, if you have a trigonal planar domain, which has 3 different ligand atoms, there can be 1 lone pair electron, creating a bent structure, as shown here. So this would be an approximate shape of the molecule. You can see the bent ligand atoms and also the lone pair electron. If you have a tetrahedral structure which has 4 domains, you actually can have 1 or 2 lone pair electron domains. If you have 1, it's called trigonal pyramidal, as you can see, a triangular pyramid with a lone pair on top. If you have 2, you can create a bent structure, which is basically a bent molecular geometry, similar to here, but with 2 lone pair electrons. So the bent structure will look something closer to this. You can see that the lone pair electrons rest on top of the molecule, while the ligand atoms rest on the bottom. Now, if you have 5 domains or 6 domains, the structures become increasingly complex. For a trigonal bipyramidal structure, you have 1, 2, or 3 possible electron domains. So here, you can see that if you have 1, it is called a seesaw structure. If you have 2 domains, 2 electron lone pair electrons, it is a T-shaped structure. And if you have 3 electron domains, it creates a linear structure where the ligand atoms are in a straight line with the lone pair electrons surrounding the central atom. Now it's important to consider when you're placing lone pair electrons on structures with 5 or 6 ligand atoms that they start with the outside electrons first on the horizontal plane, not the vertical plane. You'll never see a lone pair here, 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 and here. They're always on the outside parts of the molecule. Same thing goes for octahedral structures, slightly, because octahedral structures are different from these as they are on the top and bottom. So it's important to remember that if you have 5 domains, they're on the outside. If you have 6 domains, they're on the top and bottom. So these would be your lone pair electrons for an octahedral structure, creating a square planar. As you can see, it's a square on the same plane. Here, you have a square pyramidal. As you see, there is a square pyramid with a lone pair underneath. So quick review, if you have 2 domains for molecular geometry, linear. 3 domains, trigonoplanar. 4, tetrahedral. 5, trigonobipyramidal. And 6, octahedral. Molecular geometries will stay the same regardless of the lone pair electrons, because molecular geometries do not take into account lone pair electrons. Now, if you have 3 domains with 1 lone pair electron, it's bent. If you have 4 domains with 1 lone pair electron, it's trigonopyramidal. If you have 2, it's bent. If you have 5 with 1 lone pair electron, it's a seesaw. With 2, T-shaped. With 3, linear. And last of all, with 6 electron domain, with 6 ligand atoms, if you have 1, it's square pyramidal. If you have 2, it's square planar. Now, that last chart does seem awfully complicated. The good thing is, there's a much easier way to represent this. Hybridizations represent bonding on the central atom. So as on the previous slide, it doesn't represent bonding on the individual ligand atoms, but only on the central atom itself. In hybridizations, an ligand atom, a lone pair electron, and also multiple bonds all account for 1 domain. So if you have a lone pair electron and a ligand atom, that is 2, not lone pair electrons does not count as 2. Lone pair electron counts as 1, and this also counts as 1. So to make everything a lot easier, hybridizations, as you see, is a lot more neat than the last one that I showed you. So if you only have 2 domains, that is an SP hybridization. If you have 3, which is trigonoplanar, that is SP2. If you have 4, tetrahedral, that is SP3. 5, SP3D, and 6, SP3D2. Now, you may be wondering where the numbers 3, 2, and the D's and the S's are coming from. They represent the different orbitals that these ligand atoms, or sometimes lone pair electrons, will be in. The S orbital can only support 1 domain, which is 2 ligand atoms, or 2 lone pair electrons, as shown here. Or, sorry, this would be the S. This is the P, because each one has 2. If they were lone pair electrons, there would be 2 electrons here, 2 here, therefore creating SP. SP2 is because one of them would be the S orbital with 2 electrons. The other ones have to be P. Now, if you remember on the periodic table, elements in the P block can support a total of 6 electrons, or 3 orbitals. Therefore, this would be 4 electrons. Here you have SP3. You have 1 S cloud and 3 P clouds, totaling 2 electrons here, 6 electrons here, filling up both S and the P orbitals. The same thing goes for the trigonobipyramidal and the tetrahedral structures. You have SP3D and SP3D2. So the VSEPR theory is basically a simple way to decide and basically discern how atoms, ligand atoms, would orient themselves in a molecule to minimize repulsive forces. As shown by the balloons, it's easy to see that they will organize themselves in a way that they can get as far away as possible, which is why they're on top for this example, not maybe 4 over here, because that would create too much repulsive forces. Having 1 on top, 1 on the bottom, 3 around is the best way for them to arrange themselves in a way that minimizes the repulsive forces.